first glance, the scattered lights of the sky seem fixed in the motionless dome of the heavens. Yet over time, we see these brilliant images in constant motion. The daily crossing of the sun, the changing faces of the moon, the silent shifting of the stars. Far from being random, these motions appear in recognizable cycles, a magnificent chain of repeating events that have shaped our view of the universe. For millions of years, a lonely satellite has circled our planet in a journey that turns the days into months. But our most ancient ancestors saw more than a glowing timepiece.
Peoples would look at the moon in antiquity and see there a celestial god. It was a celestial god like any of the other celestial gods, the sun, the planets, or the stars, in the sense that it gave off light that was regarded as supernatural because it seemed to come from that object itself. The object also goes through behavior that is further evidence of its power. But in the case of the moon, that behavior took on an additional symbolic meaning. What the moon does most obviously is change its appearance.
The moon shines entirely by reflected sunlight. And as a consequence, we see the moon appear to go through a cycle of phases as it revolves around the Earth.
The question of phases really comes down to, as seen from the Earth, at that particular moment, how much of the daylight portion of the moon is facing us here on the Earth as opposed to facing away, and how much of the night side is facing us.
When the moon is on the opposite side of the Earth from the sun, the side of the moon that faces the Earth is fully illuminated. We can see the entire disk of the moon shining in sunlight, and we call that a full moon. As the moon continues along its orbit around the Earth, however, the side of the moon that faces the Earth begins to lose some of its sunlight. We see only part of that side fully illuminated. And so the moon begins to wane, it begins to wither, and it passes through a series of phases for 2 weeks until it reaches the point in its orbit where it is nearly between the sun and the Earth. And at that point, the side of the moon that faces the Earth is in complete darkness. We can't see the moon at all. We refer to that as a new moon. Of course, that lasts only a day or so. The moon continues along its orbit, and sunlight begins to creep around the edge of the moon, and we see the moon begin to wax. It begins to grow, first as a crescent, and then as a quarter, and then a gibbous phase. And 2 weeks after new moon, it's back to the side of its orbit, away from the sun, and we see a full moon again.
It takes about a month for that to happen, and that was the origin of the original month before we artificialized it in the kind of calendar that we have today.
We've used the moon to count the passing months for thousands of years, but the lunar orbit itself can be measured in 2 different ways.
Let's imagine, for example, that it's full moon. And let's also imagine that the moon is right beside a bright star in the sky. If we measure the time it takes to go from the star all the way around the sky and back to that star, and that's called the sidereal period of the moon.
The sidereal period is actually, in a sense, the real period of the moon, how long it actually takes to go around the Earth. If we wanted to measure it, what we would get for an answer is about 27 1/3 days. That's the period that's related to the amount of gravity which is attracting the Earth and the moon towards each other. That's the one that really counts. But that's not necessarily the one that most people would notice. If you were going to see any cycle to the moon at all, it would be how long it takes the moon to go through one cycle of phases, say from one full moon to the next. That's called the synodic period. It's a little bit longer. It's about 29 1/2 days to go through one cycle of phases. And this is basically how long it takes the moon to go around the Earth once with respect to the sun, because it has to be lined up with the sun in a particular way in order to be full or any other phase. And therefore the moon has to go completely around us once and then a little bit further before it can line up with the sun again and repeat its particular phase. The synodic period is valuable as a timekeeping mechanism. That's what the ancients were aware of when they talked about many moons ago. They meant the synodic period. But it was the sidereal period that eventually led us to understand how gravity works.
It's the moon's gravity that causes another familiar cycle, the daily ebb and flow of the waters that cover the Earth.
We have tides on the Earth, in the Earth's oceans, because of the gravitational attraction of the moon. And to think about that, we have to realize that the side of the Earth that is toward the moon is actually 4,000 miles closer to the moon than the center of the Earth is. And that means that the moon's gravity pulls more strongly on the oceans on the near side of the Earth than it does on the Earth itself.
And if you do that, if you try to pull something toward you while pulling harder on one side than the other, you're going to tend to stretch it as well. The solid part of the Earth doesn't stretch much, but the oceans of the Earth are fluid. They can flow very easily. And so what this differential attraction does is it pulls the water on the near side of the Earth, the side closest to the moon, away from the Earth, producing a bulge there. And then by pulling on the Earth itself harder than it pulls on the water on the far side of the Earth, it pulls the Earth away from that water on the far side, leaving a bulge of water behind on the other side. So you actually get a very symmetrical relationship, two bulges, kind of a football shape in the Earth's oceans, where the long axis of the football is pointing more or less towards the moon.
Those two bulges produce our tides because as the Earth rotates, we are carried into those bulges, and we say the tide is coming in. Actually, we're going into the tide. A few hours later, we've passed through that bulge, and we say the tides are going out. And that means we're leaving that bulge. 12 hours later, we pass through the other bulge, and we have another high tide and then low tide.
Even though we have 2 high tides and 2 low tides each day, the situation is actually a little bit more complicated than that, because the sun also exerts a tidal stretching effect on the Earth's oceans, which is about half as strong as the effect that the moon exerts.
The sun is a lot bigger than the moon is, but it's a lot further away too. So the solar tides are smaller than the lunar tides. When the Earth is positioned correctly, the moon and the sun work together to produce 2 large bulges. And then we have extreme tides. High tide is very high and low tide is very low. We refer to those as spring tides. Those occur all year round. They occur when the moon is at new moon or at full moon, because then the moon and the sun are working together to produce high and low tides.
Likewise, at third quarter or first quarter phase, when the sun-Earth line is in one direction and the moon-Earth line is in another perpendicular, the sun and moon are actually working at cross purposes with each other. One trying to stretch us this way, one trying to stretch us that way. The moon wins. The bulge always points toward the moon, but the sun's tide tends to cancel the lunar effect. And so the difference between high and low tide is very slight at those times of the month. Those are called neap tides.
Geometrically, tides are very simple, but when we put continents in the way of the moving ocean waters, we get some pretty complicated effects. Depending on the shape of the coastline, the prevailing winds, the ocean currents themselves, some places can have very high tides and other places can have rather shallow tides.
All of these things have an effect on the exact nature of the tides, but at least it's a constant effect at any given location, and we've long since learned how to predict exactly what the tides will be doing.
While tides show the dramatic effect the moon can have on Earth, another lunar cycle creates its effects in the sky.
An eclipse of the moon, also called a lunar eclipse, always occurs at full moon, when the moon becomes directly opposite the sun in the sky, so that the moon actually passes into the Earth's shadow.
It doesn't happen at every full moon, though, because the moon's orbit is tipped a little bit, and the moon often passes the Earth's shadow to the north or the south. But about twice a year, the moon's orbit is positioned just right, so the moon enters the Earth's shadow, and we have a lunar eclipse.
If the moon at full moon were to pass directly into this shadow, the moon would get very much darker as the sunlight was taken away from it. Exactly how dark depends on what part of the shadow the moon goes through. If it goes through dead center on the shadow, the darkest part, the umbra, that would be called a total eclipse of the moon. If it were to be a little bit higher or lower than the shadow and kind of graze the umbra, partly into it, partly out of it, that's called a partial eclipse. And it's also possible for the moon to not go through the umbra at all, but only through the less dark penumbral region surrounding it. That's called a penumbral eclipse. You hardly ever hear about them because the moon changes so little in noticeable brightness that most people wouldn't even notice there was an eclipse happening that night.
Lunar eclipses take quite a few hours. They're slow, unlike solar eclipses that are over in a few minutes. So you can take your time and you can set up your cameras and you can make hot chocolate and eat cookies and enjoy a lunar eclipse that will last quite a number of hours. As the moon moves into the Earth's shadow, the full moon begins to have a dark edge, and the dark edge expands and envelops the moon, and finally the moon is completely dark.
While this is happening, during the beginning part of it, as the moon gets covered further and further over, the shadow is round, the Earth is round, and so the shadow is round, and so we see a circular arc, like a bite taken out of the full moon, which gets deeper and deeper and deeper as the moon moves further into it. At first, this shadow looks black. It's so much darker than the bright, fully lit full moon that in contrast it looks completely dark.
In some lunar eclipses, the moon becomes so dark it's difficult to see against the background of stars. In many lunar eclipses, the moon glows a kind of coppery red, and that red light is actually light from the Earth's atmosphere. You can imagine where that red light comes from if you imagine being on the moon during a lunar eclipse. If you look back toward the Earth, you don't see the sun. You see the entire atmosphere of the Earth illuminated in a sunset all the way around the Earth, a ring of sunset. And the red light from that sunset illuminates the moon and makes it glow a coppery red color.
Which I'm sure contributed to the fear that our ancestors sometimes felt, the fact that it was kind of bloodish in terms of its color. This, for people who understand what's going on and aren't afraid of it, this is one of the most beautiful sights in nature, because a normal full moon looks flat, even though it's spherical. The lighting is so flat, the sunlight is going straight on, bouncing straight back, there's no shadowing, there's no relief on the surface of the moon. It looks like someone cut a picture out of a book and pasted it up there. But during an eclipse, and only during an eclipse, as the light comes from the side at a slight angle, it takes on a very pronounced three-dimensional appearance. It looks like you can actually reach up and grab it.
The moon remains in total eclipse for an hour or so, and then it moves along its orbit and continues out of the shadow, and we begin to see it emerge. First part of the moon is illuminated by sunlight, and then more and more, and within an hour or two, the moon is fully out of the shadow, and the eclipse is over.
As beautiful as a lunar eclipse can be, it pales in comparison to another spectacle of the sky, one we have watched with fear and wonder.
We have written records of observations of eclipses that go back to the 2nd millennium BC from China. So we certainly know that people have been looking at eclipses for a very long time and reacting to them. There are a few exceptions to the general conclusion people have drawn throughout the world, but most people have seen an eclipse of the moon or the sun as big trouble. Eclipses were intrusions on the concrete reality and orderliness of the universe, and when they occurred, people tried to get rid of them.
Asian cultures typically believed that a dragon was eating the sun, and they had to beat on drums to scare the dragon off. And in fact, the dragon had had its head cut off and in another Asian culture, and was up there so that it would swallow the sun.
And that's when people began to figure it was entering the jaws and going down the digestive tract of an unfriendly creature in the sky.
Our sun is 400 times larger in diameter than the moon, but it's 400 times further away. So when the moon crosses in front of the sun, we have a very spectacular solar eclipse when the moon blots out the bright surface of the sun. That probably doesn't happen on very many planets, because the moon and the sun have to be the right size and at the right distance.
If you were in space, looking down on the Earth's surface during the time that a solar eclipse were taking place, you would see exactly what you would expect. A round black spot, the moon's shadow, would be projected somewhere on the Earth's surface. That shadow can be as much as about 160 miles wide.
A satellite recording the eclipse from beginning to end will see the shadow appear at the sunrise side of the Earth, and then move slowly across. It'll take anywhere from 6 to 8 hours to go across to the sunset portion of the Earth.
Not all solar eclipses are the same. If you happen to be standing in the path of the shadow of the moon, you're in the path of totality, and you'll see a total solar eclipse. The moon's shadow sweeps over you, and the bright surface of the sun is completely hidden, and you see a total eclipse. But if you're outside that path, then you see part of the sun peeking around the moon. You're in the penumbra of the moon's shadow, and then you see a partial eclipse.
If you got more than a few thousand miles away from that spot, you wouldn't see an eclipse at all. Even though there's an eclipse happening that day, you're sufficiently off-center that, from your point of view, the sun and the moon are not lined up, and the moon doesn't cover the sun at all.
Sometimes we have a solar eclipse when the moon is in the further part of its orbit. The moon's orbit is elliptical. And when it's a little bit further away from the Earth, it can be too small to hide the sun, and we see a circle of sunlight around the moon. It's an annulus, and we refer to that as an annular eclipse. Annular eclipses are interesting, but they're not very exciting. Total eclipses are the big show in solar eclipses.
Total solar eclipses are a wonderful and spectacular method for seeing phenomena that we cannot otherwise see. Specifically, we can see very well the chromosphere, which is the layer above the white light layer that we can see every day, and even more so, we can see the corona, which is much fainter than the white light layer, the photosphere, and study both those layers in detail in a manner that you pretty much have to do either during a total eclipse or be out in space to do.
As the eclipse begins, there are a number of phenomena that can occur. One of them, for example, is called Bailey's beads. Either at the beginning of the eclipse or at the end of the eclipse, a small portion of the sun's brilliant surface can peek through a valley on the edge of the moon, and suddenly, for just a moment, you may see a brilliant, glowing string of beads along the edge of the moon.
The last one of those beads, and especially if you have a nice deep valley where all the others have gone away, can become this diamond ring. You see a brilliant bit of white light staring at you with the much softer glow, white as well, pearly glow, of the corona surrounding it, and that's called the diamond ring. You get one at the onset of totality and at the end of totality if you're lucky.
But there's another beauty in eclipses, and that is in the pattern that they make. Eclipses occur during certain eclipse seasons. They follow a pattern.
Eclipses of the sun occur at new moon. Eclipses of the moon occur at full moon. We have one new moon and one full moon every single month, and yet we don't have eclipses every single month. The reason has to do with the fact that as the Earth goes around the sun once a year in its orbit, that orbit remains within a single flat zone, a single plane, called the ecliptic plane. And as the moon goes around the Earth once a month, it too occupies a plane which is tilted by about 5 degrees relative to the Earth's orbit around the sun.
Since the sun follows the ecliptic, that means the moon has to be crossing the ecliptic for an eclipse to occur. The location in the moon's orbit where the moon crosses the ecliptic is called a node of the moon's orbit, and there are 2 of them on opposite sides of the sky.
The moon goes around once a month, so it passes a node every 2 weeks. But the sun takes a year to go around the sky, and so it only passes a node every 6 months. And so every 6 months you have an eclipse season during which a moon in the new or full phase will result in an eclipse. At new phase, it'll pass in front of the sun to produce a solar eclipse. At full phase, it'll pass into the Earth's shadow to produce a lunar eclipse.
It's a complicated pattern, but it repeats. And there's a cycle of eclipses that repeats every 18 years or so. That pattern is called the Saros cycle.
Basically, the Saros cycle is related to the approximately 18 years that it takes the moon's orbit to wobble. Like throwing a quarter onto a table on its edge. It kind of does this for a few minutes before a few seconds before it settles down. The moon's orbit does the same thing.
The ancient Greeks, perhaps even the Chaldeans, could predict eclipses because they recognized that cycle, the Saros cycle. They had no idea what the sun was or what the moon was or what an eclipse was, but they recognized the pattern that the eclipses made, the Saros cycle, and that meant that they could predict eclipses.
Astronomers have recorded and predicted eclipses for centuries, but few of these celestial alignments can match the spectacle and drama of a total solar eclipse.
If you can get to an eclipse of the sun, do so. You may have to travel thousands of miles to put yourself in the path of totality, but the experience is really worth the effort, because a total eclipse of the sun is really a beautiful experience.
It wasn't until 1991 that I finally got a chance to see a total solar eclipse myself in person. I saw the one that was visible from Baja and a number of other places on the Earth. That I was in Baja. And it was, as everybody has been telling me, the most fantastic sight in nature.
In preparing for a solar eclipse, there's a lot that goes into it. First of all, one has to find out where the eclipse is going to be, and then look at the weather. You do try and pick at least the areas that are most likely to have good weather. In the process of selecting the eclipse and the site, you also decide on what equipment to bring along. It can range anywhere from cameras to spectrographs to video imaging equipment. You have to have the filters necessary to protect the equipment and eyeballs from the partial eclipse when the sun isn't covered. And then all this material has to get packed up, shipped maybe weeks in advance to arrive in time to be shipped out to the middle of nowhere, set up, and you spend those days, maybe weeks before the eclipse out there getting set up, getting ready, rehearsing the activities that are go on during the eclipse, and then finally eclipse day arrives and you hope that the weather is going to behave for you and you have a good set of measurements. A total eclipse really starts with an average regular day. There's nothing unusual about it except that maybe an hour or so before totality there's a little notch, a bite taken out of the sun, and I at least feel like I have a moment of relief when, aha, it's happening right on time just the way it's supposed to. And for the next 45 minutes to an hour, all that happens is that the sun gets eaten up by the moon.
And as time passes, the moon moves further across the sun, and over a period of an hour or two, the moon begins to blot out larger and larger portions of the sun. It's still mostly broad daylight. Your eyes open to adjust to the dimming light, and you don't really notice that anything is happening unless you're really paying attention to the sun.
Among the things that happens in those last few minutes, the lighting gets much darker. It's like a very heavy overcast, except there's no clouds, and so you still have shadows. And the shadows are unusual because the sun isn't symmetrical anymore. It's a long, narrow thing, a crescent, rather than a round object. And so if you were to put your hand out and look at the shadow on the ground, you would see it would look fuzzy in certain directions, but it would be very sharp in other directions, depending how you oriented it relative to the crescent sun.
And you may even see little crescents on the ground, pinhole projections of the sun. In fact, nature sometimes does the job for us by providing pinhole images through leaves in trees. Many leaves will overlay each other, and sometimes you get a pinhole of light that comes down, projects onto the ground. It's cooler, too. The temperature is dropping. There's a certain sense of anticipation, which is more in the emotional range than anywhere else. But birds and other animals also do seem to notice that things are changing.
We all noticed that the ants that had been so plentiful during all morning long suddenly disappeared as totality approached. And the cows came home. There was a cow pasture not very far away, and all of a sudden they were lined up bumper to bumper heading back to wherever they go at sunset.
You look towards the west, you see that it's much darker in that direction. You turn around and it's just as bright along the horizon as you were expecting it to be. And you realize, aha, the shadow is coming.
You get this overwhelming feeling because of the speed of all this that you're about to be engulfed by something that you have no control over. Like you're standing on a track with a freight train coming down and your feet are nailed to the track. Because you're about to be engulfed by the shadow, which you can actually see extending out of the sky. It's rushing toward you at 1,000 miles per hour.
Now you can't actually keep track of all that's going on. You can't be looking all the directions that you'd like to be. You might be looking up, trying to see how early you can see the corona. Are there any large prominences visible? You're looking for the diamond ring effect and Bailey's beads before that. And so all these things are going on in that last couple of minutes.
The real spectacle, of course, comes when the sun is completely covered over. That's the total eclipse, the total phase of the total eclipse. This only lasts for about 7 minutes at the longest. The sky gets a very dark blue. It's like a deep twilight. You can actually see the brighter planets and stars during the daytime. The corona is brilliant, pearly white. The corona is not subtle. It's actually about as bright as the full moon. It's just that the normal sun is 500,000 times brighter than that, which is why you don't normally see the corona. And that bright white light is in stark contrast to the silhouette of the moon, which really is black. It's like the blackest black that you'll ever see. There's no reflected light coming from that direction at all. It's like somebody punched a hole in the sky. And I was also surprised and delighted by the prominences that we were hoping to see. And so I was looking at the prominences under magnification, much easier to see then, and reminded that they're always there. I mean, they look violent. The sun seems to be seething, except it's only during a few minutes of totality that you can actually see this.
And then it's all over. In a flash, you get a diamond ring again. Maybe you've got some prominences. Again, which direction you're looking matters. It all unreels the other way, like a movie going backwards. People return to trying to settle down after a very exciting few minutes. And you watch the eclipse end. Finally, the sun is back whole, and it's like nothing happened.
The motions of the Earth and Moon create fantastic spectacles in the sky. An endless parade of events that occur with such regularity, we mark time in their rhythms. Some we see every day. Others we witness only by chance or with great effort. But these patterns provide more than celestial drama. They are cycles of the sky that profoundly affect life on Earth.